Welcome to Chemistry, Functional Groups in Organic Chemistry. Functional groups are specific groups of atoms within molecules that determine the characteristic chemical reactions of those molecules. They are the reactive centers of organic compounds, defining how molecules interact with each other. In this presentation, we will explore alcohols, ethers, aldehydes, ketones, carboxylic acids, esters, amines, and amides. We will cover their structures, properties, naming conventions, and reactivity. Through 5 quiz questions and 5 detailed problems, you will learn to identify, name, and predict the behavior of these essential organic functional groups. A functional group is a specific arrangement of atoms in an organic molecule that determines its chemical properties and reactivity. The same functional group will undergo similar chemical reactions regardless of the rest of the molecule's composition. This principle allows chemists to predict the behavior of organic compounds systematically. For example, all alcohols contain the hydroxyl group bonded to a carbon atom and exhibit characteristic reactions such as oxidation to aldehydes or ketones. The concept of functional groups is fundamental to organic chemistry classification. The R group notation represents the variable hydrocarbon chain to which the functional group is attached. Alcohols contain the hydroxyl functional group OH bonded to a saturated carbon atom. The general formula is ROH, where R is an alkyl group. Alcohols are classified as primary, secondary, or tertiary depending on the number of carbon atoms attached to the carbon bearing the hydroxyl group. Methanol, ethanol, and isopropanol are common examples. The hydroxyl group is polar due to the high electronegativity of oxygen, allowing alcohols to form hydrogen bonds. This gives alcohols higher boiling points than comparable alkanes. Smaller alcohols are soluble in water because the hydroxyl group can form hydrogen bonds with water molecules. Alcohols undergo oxidation reactions. Primary alcohols oxidize to aldehydes, then to carboxylic acids, while secondary alcohols oxidize to ketones. Ethers have the general formula ROR', where 2 alkyl or aryl groups are bonded to an oxygen atom. The COC bond angle is approximately 110 degrees. Ethers are relatively unreactive, making them excellent solvents for organic reactions. Diethyl ether, often simply called ether, was historically used as an anesthetic. The oxygen atom in ethers is weakly basic and can form hydrogen bonds with water, giving ethers moderate water solubility. Unlike alcohols, ethers cannot form hydrogen bonds with each other because they lack an OH bond. This results in boiling points that are lower than alcohols of similar molecular weight. Ethers are sensitive to oxidation, forming explosive peroxides upon prolonged exposure to air. Aldehydes and ketones both contain the carbonyl functional group, which is a carbon double bonded to oxygen. In aldehydes, the carbonyl carbon is bonded to at least one hydrogen atom, with the general formula RCHO. In ketones, the carbonyl carbon is bonded to 2 carbon atoms, with the general formula RCOR'. The carbonyl group is highly polar due to the electronegativity difference between carbon and oxygen. The carbon carries a partial positive charge and is electrophilic, while the oxygen carries a partial negative charge and is nucleophilic. This polarity makes carbonyl compounds reactive toward nucleophilic addition reactions. Formaldehyde, acetaldehyde, and benzaldehyde are common aldehydes. Acetone and butanone are important ketones used as solvents. Aldehydes are generally more reactive than ketones due to less steric hindrance. Carboxylic acids contain the carboxyl functional group, which combines a carbonyl group and a hydroxyl group on the same carbon. The general formula is RCOOH. The carboxyl group is highly polar and can form strong hydrogen bonds. Carboxylic acids are weak acids that partially dissociate in water to give carboxylate anions and hydronium ions. The acidity is due to resonance stabilization of the carboxylate anion, where the negative charge is delocalized over both oxygen atoms. Esters have the general formula RCOOR' and are derived from carboxylic acids by replacing the hydroxyl hydrogen with an alkyl group. Esters are responsible for many fruit flavors and fragrances. The formation of esters from carboxylic acids and alcohols is called esterification, which is an equilibrium reaction catalyzed by acid. Amines are derivatives of ammonia, where one or more hydrogen atoms are replaced by alkyl or aryl groups. The general formulas are RNH2 for primary, R2NH for secondary, and R3N for tertiary amines. Amines are basic because the nitrogen atom has a lone pair of electrons that can accept a proton. Aliphatic amines have pKb values around 3 to 4, making them stronger bases than ammonia. Amides have the general formula RCONH2 and are derived from carboxylic acids by replacing the hydroxyl group with an amine or ammonia. The amide bond is planar due to resonance between the carbonyl and the nitrogen lone pair. This resonance makes the CN bond have partial double bond character. Amides are much less basic than amines because the nitrogen lone pair is delocalized into the carbonyl group. Proteins are composed of amino acids linked by amide bonds, also called peptide bonds. Understanding reactivity patterns is crucial for predicting organic reactions. Nucleophilic addition is characteristic of carbonyl compounds, where a nucleophile attacks the electrophilic carbonyl carbon. Nucleophilic acyl substitution occurs with carboxylic acid derivatives, where the carbonyl carbon undergoes substitution of the leaving group. Elimination reactions can occur in alcohols through dehydration, producing alkenes. Oxidation and reduction reactions transform functional groups. Primary alcohols oxidize to aldehydes, then to carboxylic acids. Aldehydes oxidize to carboxylic acids. Carboxylic acids reduce to primary alcohols. The reactivity order of carboxylic acid derivatives toward nucleophilic acyl substitution is acyl chlorides, anhydrides, esters, then amides. Functional group interconversion is a fundamental strategy in organic synthesis. Quiz question 1. Which functional group contains a carbonyl carbon that is bonded to both a hydroxyl group and an alkyl group? Option A, alcohol. Option B, aldehyde. Option C, ketone. Option D, carboxylic acid. Take a moment to think about your answer. The correct answer is D, carboxylic acid. The carboxyl group RCOOH has a carbonyl carbon bonded to both a hydroxyl group and an alkyl group, giving carboxylic acids their unique acidic properties. Quiz question 2. When a primary alcohol undergoes oxidation, it first forms which functional group? Option A, ketone. Option B, aldehyde. Option C, ether. Option D, carboxylic acid. The correct answer is B, aldehyde. Primary alcohols first oxidize to aldehydes. Then, with further oxidation, they become carboxylic acids. Quiz question 3. Which of the following compounds has the highest boiling point? Option A, propane. Option B, methyl ethyl ether. Option C, 1-propanol. Option D, propanol. The correct answer is C, 1-propanol. 1-propanol has the highest boiling point because it can form strong hydrogen bonds through its hydroxyl group. The ether and aldehyde have weaker intermolecular forces, and propane only has London dispersion forces. Quiz question 4. The amide functional group is important in biochemistry because it forms what? Option A, the glycosidic bond in carbohydrates. Option B, the peptide bond in proteins. Option C, the phosphodiester bond in DNA. Option D, the ester bond in triglycerides. The correct answer is B, the peptide bond in proteins. The amide bond links amino acids together in proteins and is also called the peptide bond. Quiz question 5. Fischer esterification is the reaction between what? Option A, an alcohol and an aldehyde. Option B, a carboxylic acid and an alcohol. Option C, an amine and a ketone. Option D, an ether and a carboxylic acid. The correct answer is B, a carboxylic acid and an alcohol. Fischer esterification is the acid-catalyzed reaction between a carboxylic acid and an alcohol to form an ester and water. Problem 1. Identifying functional groups. Identify the functional groups present in aspirin, also known as acetyl salicylic acid, with the formula C6H4OCOC3COOH. Step 1. Aspirin formula is orthoacetoxybenzoic acid, C6H4OCOC3COOH. Step 2. The COO group is a carboxyl group, which is the carboxylic acid functional group. Step 3. The OCOH3 group is CH3COO, which is an ester functional group. Step 4. The benzene ring C6H4 is aromatic but not a distinct functional group for this problem. Step 5. Therefore, aspirin contains both a carboxylic acid and an ester functional group. The answer is ester and carboxylic acid. Problem 2. Alcohol classification. Classify each alcohol as primary, secondary, or tertiary. A. CH3, CH2, CH2OH. B. CH3, 2, CHOH. C. CH33COH. Step 1. Find the carbon atom directly bonded to the OH group in each compound. Step 2. For A, CH3CH2, CH2OH, the OH carbon is CH2 bonded to one CH3CH2 group and two hydrogen atoms. Step 3. The OH carbon in A is bonded to only one other carbon, so it is primary. Step 4. For B, CH32CHOH, the OH carbon is CH bonded to two methyl groups and one hydrogen. Step 5. The OH carbon in B is bonded to two other carbons, so it is secondary. Step 6. For C, CH33COH, the OH carbon is C bonded to three methyl groups with no hydrogen atoms. Step 7. The OH carbon in C is bonded to three other carbons, so it is tertiary. The answer is A primary, B secondary, C tertiary. Problem 3. Carboxylic acid strength. Calculate the pH of 0.100 molar acetic acid solution with Ka of 1.80 times 10 to the minus 5. Step 1. Write the equilibrium for acetic acid dissociating into acetate ion and hydrogen ion. Step 2. Initial concentrations are 0.100 molar for the acid, 0 for hydrogen and acetate. Step 3. Set up an ice table and let X equal the hydrogen ion concentration at equilibrium. Step 4. Ca equals X squared over 0.100 minus X equals 1.80 times 10 to the minus 5. Step 5. Since Ca is small, assume 0.100 minus X is approximately 0.100. Step 6. X squared equals 1.80 times 10 to the minus 5 times 0.100, which is 1.80 times 10 to the minus 6. Step 7. X equals the square root of 1.80 times 10 to the minus 6, which is 1.34 times 10 to the minus 3 molar. Step 8. pH equals negative log of 1.34 times 10 to the minus 3, which equals 2.87. The approximation is valid at 1.34%, which is less than 5%. The answer is pH equals 2.87. Problem 4. Esterification. What ester is formed when propanoic acid reacts with methanol in the presence of concentrated sulfuric acid? Step 1. Fischer esterification is the reaction between a carboxylic acid and an alcohol to form an ester and water. Step 2. Propanoic acid is CH3CH2COOH and methanol is CH3OH. Step 3. The OH from the carboxylic acid and the H from the alcohol combine to form water. Step 4. The remaining fragments join CH3CH2CO from the acid and OCH3 from the alcohol. Step 5. The product is methylpropanoate CH3CH2COOH3 plus water. The answer is methylpropanoate CH3CH2COOH3. Problem 5. Amine basicity. Calculate the pH of 0.0500 molar methylamine solution with Kb of 4.40 times 10 to the minus 4. Step 1. Write the base equilibrium for methylamine reacting with water to form methylammonium and hydroxide. Step 2. Initial concentration of methylamine is 0.0500 molar. Hydroxide and methylammonium are 0. Step 3. Let X equal the hydroxide concentration at equilibrium. Step 4. Kb equals X squared over 0.0500 minus X equals 4.40 times 10 to the minus 4. Step 5. Solve the quadratic equation. Step 6. X squared plus 4.40 times 10 to the minus 4x minus 2.20 times 10 to the minus 5 equals 0. Step 7. Using the quadratic formula, X equals 4.63 times 10 to the minus 3 molar for hydroxide. Step 8. pOH equals negative log of 4.63 times 10 to the minus 3, which is 2.33. Step 9. pH equals 14.00 minus 2.33, which equals 11.67. The answer is pH equals 11.67. Let us consolidate everything we have learned about functional groups. A functional group is a specific atomic arrangement that determines a molecule's chemical properties. Alcohols contain the hydroxyl group and are classified by carbon substitution, primary, secondary, or tertiary. The hydroxyl group allows hydrogen bonding, giving alcohols high boiling points. Ethers have an oxygen atom bridging two carbon chains. They are excellent solvents, but can form dangerous peroxides. Aldehydes and ketones contain the carbonyl group and undergo nucleophilic addition reactions. Aldehydes are more reactive and can be oxidized to carboxylic acids. Carboxylic acids contain the carboxyl group and are weak acids due to resonance stabilization of the conjugate base. Esters are derived from carboxylic acids and are responsible for many fruit flavors. Amines are basic nitrogen compounds classified by degree of substitution. Amides contain the carbonyl group bonded to nitrogen and form the peptide bonds in proteins. The carbonyl group is arguably the most versatile functional group in organic chemistry, participating in addition, substitution, and condensation reactions. Thank you for studying organic functional groups with us.